Alright everyone, welcome back. We're talking about chapter 2 still. This is mainly 2.2. Right, limits, introduction to limits, definition of limits, how to calculate limits. So specifically here in this section, we're going to be talking about, say we don't have a graph. Okay, with a graph it's easy. You look at where the function's heading as x gets closer and closer to some value. But let's say you don't have a graph, or you don't feel like graphing it, or you can't graph it. How do you do this stuff by hand? So this is basically what we're starting with here. All right, limits by hand. And how I want to start is by a little example, just to kind of help us out with some basic things. I mentioned last time that if a function is continuous, then the limit is basically just plugging in the value, right? So let's consider this function, f of x equals x squared, okay? And we want to consider, right, the limit as x goes to 2 of x squared. So I could make my table, with x over here, x squared over here, and put things in that are really close to 2, right? So say I'm using a calculator here to figure this out, but 2.01 squared gives me 4.0401. 2.001 squared is going to give me 4.004001. And if I take it one step further, that's where we'll stop, I think. If I do 2.0001, that squared is 4.00040001. And we get this pretty clear pattern. We can check it from the other side. In fact, you probably should. I'll let you do that. But basically, we see that x squared goes to 4 as x goes to 2. And that makes sense, right? As x gets closer and closer and closer to 2, x squared should get closer and closer and closer to 4. And that's since, right, 2 squared is 4. As x gets closer and closer to this actual value of 2, the result should get closer and closer and closer to this actual result 4, right? So we say that the limit is equal to 4. And we could even go further and just plug the value in and say that the limit as x goes to 2 of x squared is 2 squared, which is 4. Okay. So we're going to use this idea as we go along. It's going to help us out a bit. But if we have a very basic function that's nice and continuous, basically we can just plug in the value. Right? We can plug in that 2. Right? So that's basically if the function is continuous. So what we're going to be talking about here is how to make this a bit more powerful. I have, right, the limit of x squared. Let's say I wanted limits of sums or of products or of quotients, and so that's what we are going to look at now, are some various limit laws or limit rules. Okay, so basically these are techniques for computing limits algebraically. This is saying this is 2.3, but it's also in 2.2 as well. It's all kind of interconnected, as we'll see. But basically, for the following limit rules, what we're going to do is we're going to be looking at limits as x goes to a of f of x and limits as x goes to a of g of x. And we're going to assume that they exist. And for some of these, we need C, the letter C, to be constant. And we need M and N, both greater than 0, to be integers. All right, this is just some house cleaning just to make sure we have everything the way we need it. Okay, so here are our limit laws. All right, this one, if I want to take the limit as x goes to a of f of x plus g of x, so a sum of functions, well, I can just distribute this limit sign across and instead take the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Right? So if I know the limit of f and g separately, well, I can split the limit across the sum like that. Similarly, let's say I want to find the limit of a constant times f as x goes to a. Well, I can actually drop that limit past the constant because the constant is not going to affect things that much. If we think about our previous example, right, since the limit as x goes to 2 of x squared is 4, right, well, we can pretty much assume from this that the limit as x goes to 2 of, let's say, oh, I don't know, 1, let's make it a little simpler. Let's make it 3 times x squared. Right? Well, that's just going to be 3 times the limit as x goes to 2 of x squared, which will be 3 times 4, or 12. Okay? So that constant doesn't really affect what's going on with the x's, right? It doesn't cause any trouble. It just, no matter what number we get, we multiply by that 3. Okay? And these other rules are very similar, right? If the limit as x goes to a of f of x times g of x, well, I can actually take these separately and take the product. So the limit of the product will be the product of the limits. So the limit of f times g will be the limit as x goes to a of f times the limit as x goes to a of g. And the same with division. Okay, the limit as x goes to a of f of x over g of x is actually the limit as x goes to a of f of x over the limit as x goes to a of g of x. And this is provided that this limit on the denominator is not equal to 0, since we can't divide by 0. Okay. All right, let's look at an example. Oh, actually, a couple more rules, sorry. And these rules should feel nice, right? They work how we would like them to, which is pretty nice, I think. In this case here, the limit as x goes to a of f of x to the n, where remember n was a positive integer, I can actually move the limit inside beneath that power and instead do the limit as x goes to a of f of x raised to the n. And we can do the same thing, right, if I have a fractional power. And this is provided f of x is greater than or equal to 0 for x near a, and if m is even, or if m is even, right, because if m is even, we need what's in here to be greater than or equal to 0. And if n over m is reduced to lowest terms, all right, that's just covering our tracks, right? We just need to make sure that the limit exists. We need to make sure that everything's nice and continuous. Here, for the next two rules, we assume that p and q are polynomials, and basically the limit as x goes to a of a polynomial p of x is just plugging a into the polynomial, right? Plugging in a. Right, that's pretty big. And then here, again, if I have a fraction of polynomials, say the limit as x goes to a of p over q, that's just going to end up being p of a over q of a, provided q of a is not 0. That should be not equal to 0. Okay. Same idea. We just plug it in, provided everything exists. And this is a sneak peek that I talked about last time. I've talked about it a little bit today. But basically, if f of x is continuous at x equals a, right, then the limit as x goes to a of f of x is going to be equal to f of a. Okay? If you think about it, for a function to be continuous, right, its graph has to be nice like this. And if this is a, right, its limit from both sides is going to f of a. Right? So the limit and the function value will match, provided the function is continuous. Okay, so these are our limit rules so far. Let's look at some examples of how we work with these. Right? Alright, so for this example, what we're going to do is suppose that the limit as x goes to 3 of f of x is equal to 3. The limit as x goes to 3 of g of x is equal to 4. And the limit as x goes to 3 of h of x is equal to 7. So we're going to use the limit laws to compute each limit. Okay, so for this first one, I'm definitely going to take this step by step, step by grueling step. Okay, you don't usually have to do this. All right, and in fact, in the next couple examples, I won't. But for this very first one, I want to show you how each limit law is used. So, for example, what I have here is the limit as x goes to 3 of f of x minus g of x over h of x. So what we really have is a quotient. And we have a fraction of stuff there, top and the bottom. So we have that limit law that says that this will be the limit as x goes to 3 of the top all over the limit as x goes to 3. Sorry, messed that up. Of the bottom down here. Provided that that denominator doesn't equal 0 when we crank out that limit. That would be the big problem. All right, and now up top I actually have a difference. I have the limit as x goes to 3 of f of x minus g of x, and there I can say that that will be the limit as x goes to 3 of f of x minus the limit as x goes to 3 of g of x. And this is still all over the limit as x goes to 3 of h of x. And now we can start plugging things in, right? The limit as x goes to 3 of f of x, we know that is 3. Right? And I know that the limit as x goes to 3 of g of x is 4. And I know that the limit as x goes to 3 of h of x is 7. So what we end up with is negative 1/7. Okay. All right, so for this next one, I have the limit as x goes to 3 of f of x times g of x plus 2 times h of x. Now, what I meant last time mean, last time is, right, we didn't really have to write all these steps. It helps us learn the rules, right? But we could have jumped right here to just 3 minus 4 over 7, right? So we could actually here write that this is the limit as x goes to 3, because we can distribute it across the sum, and we can distribute it across all the multiplications and get the limit as x goes to 3 of f of x times the limit as x goes to 3 of g of x plus 2 times the limit as x goes to 3 h of x. Or you could actually just jump right to, right, this is going to be 3, because that's the limit as x goes to 3 of f of x, times, blocking it here, 4, right, that's the limit as x goes to 3 of g of x, plus 2 times 7, which is the limit as the limit as x goes to 3 of h of x. Right. So this, when we calculate it out, 3 times 4 plus 2 times 7 ends up being 26. Hopefully, if my math is right. And then this last one, the limit as x goes to 3 of g of x all cubed, well, that's just going to be the limit as x goes to 3 of g of x all cubed. We can move that limit inside. And the limit as x goes to 3 of g of x, we know by now, is 4. So this is going to be 4 cubed, which is 64. Okay. So not too bad so far, right? If we're told what the limits are, we just kind of plug them in. And here, again, we could have skipped this step, jumped right to this one. When you're working these problems for a grade, don't just go straight to 64. I want to at least see that you know what you're doing here, that you're plugging in a value, that you're replacing it. You don't have to write every single step like we did up here, but I do, at the very least, want to see this step, 3 minus 4 over 7. Okay, so I know that you at least got that part of the idea. Okay, so now we are going to actually try and crank out a couple of limits. Okay. So first of all, let's try the limit as x goes to 2, okay, of x squared minus 4x all over 5x cubed minus 30. Right. So in my experience, the first thing you want to do, okay, is try plugging in the values. Right? Just try plugging in the numbers and seeing what you get. Okay? And specifically what you're looking for, if the denominator, okay, if the denominator ends up being 0, that's usually the time you'll have trouble. Okay? But if I plug 2 into the denominator here, I'll get 5 times 2 cubed, right, which is 8, right? So that will be 40 minus 30. This is not equal to 0, so we should be fine, right? But let's just try and plug it in. So if I plug in 2, looks like the camera's not picking that up very well. Let me do that underneath here. If I plug in 2, that will be 2 squared minus 4 times 2 all over 5 times 2 cubed minus 30. Right? So that's going to be 4 minus 8 all over, right? And that, as I said, that's 40 minus 30, which will be negative 4 over negative 10. Right, so that's 2/5. Okay. And again, I like to see this step, so I at least get a sense that you are plugging everything in and you're checking it out. And from here, you can really just jump right to here. All right, I assume you know how to multiply and, you know, raise things to exponents by this point. All right. So that's your first line of defense. That's your first strategy. Plug the value in. Do you get an answer out? Okay. If not, well, that's actually what we're going to be talking about for the rest of this section. That's what makes this, you know, able to have an entire chapter on limits, is what happens when we get division by 0. All right, so let's look at another example. All right, so let's try this limit here. Let's say the limit as x goes to 2. They won't all be going to 2. Let's say the square root of x cubed plus 1 minus 3x plus 1 all over 5x plus 2. So you can see that it's coming out okay. Right. Now again, like I said, let's try plugging into the denominator and seeing what happens. If I plug 2 into the denominator, I'm going to get 10 here, right, plus 2, so that's 12. Denominator is definitely not equal to 0. All right, so we can pretty much just proceed, you know, normally. Another thing to check is, would we put a negative underneath this square root? That's another thing to check, because that would also give you something that's undefined. So basically you're looking for things that are, you know, going to exist and be nice. And again, here, you plug in 2 here, you're going to get 8 plus 1. That'll be nice and positive, exactly what we want. So we can go ahead and just plug 2 right in. And you can, you know, skip this a little bit. That'll be, right, 8 plus 1 minus 6 plus 1. You know, it might help initially if I just say that this is 2 cubed plus 1 minus 3 times 2 plus 1 all over 5 times 2 plus 2. Okay, usually you don't have to write every little thing here, but just so you know, we are just taking all of our x's and replacing them with 2's at this point. Okay, so this is going to end up being square root of 9 minus 5 over 12. Okay, so that's 3. So we're going to end up with negative 2 over 12, which is negative 1/6. Okay. So again, your first line of defense, your first strategy for limits, right? Plug and chug. Plug it in, see what you get. Right. Right, let's look at another example. Let's look at, so the limit as x goes to negative 4, there we go, there's another value there, of x squared minus 16 all over x squared plus 2x minus 8. Okay, so for this one, what we have to be careful about is when we check, right, our denominator. Well, first of all, if I plug negative 4 into the numerator, negative 4 squared is 16. I get 16 minus 16, so the top ends up being 0. Okay, and then the denominator, well, we're going to get a similar problem. Negative 4 squared is 16. Okay, then plus 2 times negative 4, so that will be negative 8. So I'll get 16 minus 8 minus 8. That will also be 0. Denominator here goes to 0, and so does the top. This is a 0 over 0 case. I'll write that over here. 0 over 0 case. This is a very, very common case. Okay, and don't ever write that 0 over 0 is equal to 0. 0 over 0 is undefined. So what does that mean? Does that mean we give up? Does that mean we stop? Well, absolutely not. I can't plug in the values. That's our first strategy. Our second strategy is maybe we can do something about this. Okay. Looking at this, just the way it looks like the top and the bottom can both factor. Okay. So when I do that, let's say that this is, now look at what I'm doing here. Got to make sure you write this limit sign every single time. I will take off for this. Okay. If you start with a limit, you've got to keep a limit, and you keep writing limits until x's disappear. Let me say that again. You keep writing limits until x's disappear, because all I'm doing from this step to this step is factoring, right? So x squared minus 16, that factors into x plus 4 times x minus 4. Since there are still x's over here, I have to write my limit sign, right? So then the denominator will also factor. Let's see, we would want factors of negative 8 that sum up to be 2. So I'm thinking 4 and negative 2 will do that. Okay. So now I've changed my problem, so that's the limit as x goes to negative 4 of x plus 4 times x minus 4 all over x plus 4 times x minus 2. And now the x plus 4's will cancel, and I'm left with the limit as x goes to negative 4. Notice I'm writing the limit sign again. X goes to negative 4 since I have x's here. And now I have a limit as x goes to negative 4, x minus 4 all over x minus 2. And check it out, when I plug in the negative 4 in the denominator, now this doesn't go to 0. Right? It's going to go to negative 6. Right? So when I plug in negative 4, I'll get negative 8 over negative 6. Okay? Which ends up being 4/3. All right. Now, I want to show you a little something here. I basically just said, hey, we can factor and it works out. But let's take a closer look at this example. Okay. Here's a table that I made of this very same problem. Right? And I looked at my x's as x got really close to negative 4. Okay. From one side and from the other. So as say starting at negative 4.01 all the way up to negative 4.000001, and also from the other side negative 3.99 all the way up to 1, 2, 3, 5, 6 nines after the decimal place. And what we see is it looks like as x gets closer and closer and closer to negative 4, right, f of x is getting closer and closer and closer. Well, it looks like, looking at the pattern on both sides, 1.33333, so 1.3 repeating, and lucky for us, that actually ends up being 4/3. Now you might think, well, why can't we just use a table every time, right? Why can't we always do that instead of, this other way we've started analytically using factoring and whatnot? Well, the reason for that is because, one, it takes a long time to make tables like this. You notice here that I have this pre-made because actually sitting down and finding all these values is extremely tedious, and you actually have to find a bunch to make sure you have a pattern. Okay, so for example, so let's look at this function, f of x equals cosine of 1 over x. Okay. Right? And let's say I want to find the limit as x goes to 0 of this function. So I start with my table, right? I let values get closer and closer to 0. So I start at 0.001 and I get 0.56238. Okay, that's fine. And then at 0.0001, I get negative 0.95216. Okay, so I went from positive to negative. Then I throw in another 0, right? And I get negative 0.99936. Oh, it looks like this is going to -1, right? Right? That's what it looks like from these three values. Well, actually wrong. Because when we start adding more values to this table, say I add another 0 in to get 0.000001, suddenly I'm up to the positive 0.93675. And then I throw in another 0, and now we're back down to negative 0.9. And then I put in another 0, and now it's negative 0.36. What is going on? Right? There's no pattern emerging. Okay? Using a pattern, we see that there is no, using a table here, we see that no pattern showing up. And this is why tables aren't a great way to evaluate limits. Okay? This function has no limit at 0. Right? The limit at 0 is actually undefined. Here's what the graph looks like of this function. Okay? Here we're at very small values here. This is 1 over 2 pi. This is 1 over 4 pi. And you see as x gets closer and closer to 0, from the right, we have oscillations back and forth. Cosine of 1 over x goes back and forth from -1 to 1. And as it gets closer and closer to 0, it starts oscillating faster and faster and faster. And there's no number, right, that this function gets closer and closer to. Right? The limit does not exist since there is not a single value that this function gets closer and closer to. Right? That's what we need for the limit to exist, right? We need, as x gets closer and closer to 0, we need f to get closer and closer to a number, and here, that's not happening. Here it's just kind of squishing into making a big sludge here between -1 and 1. Right? It just, yeah. So that's why we can't use a table. That is why we are actually trying to find other ways, right, to calculate limits. Right, so here let's look at another example. Okay, let's look at the limit as x goes to 2 of x cubed minus 8 all over x minus 2. Okay. And another one where x goes to 2. All right. So in this case, Once again, if I try and plug in 2, check the denominator, we get the denominator here is actually going to 0. And actually, so is the numerator. The numerator, when we plug in 2, we'll get 8 minus 8. This also goes to 0. So I'll say that this is the 0 over 0 case. Don't write that this is actually equal to 0 over 0. You'll get a lot of math teachers fuss at you for that. Okay. So what we're going to do, since we can't plug in the value, right, that's our first line of defense, that's our first strategy. What we're going to try now, our other trick, is let's factor. Okay? Factor. So remember, I write my limit sign again. And I can actually factor the top, and a lot of people don't remember this particular rule. This is the difference of cubes. Okay. Right, we have a factoring method for that, a cubed minus b cubed, and that's going to factor into a plus b, oops, excuse me, sorry, a minus b. A minus b times a squared plus ab times b squared. All right, so a here is, of course, x, b is 2. So this will factor into x minus 2 times x squared plus 2x plus 4, right? Because b squared, b is 4, or excuse me, b is 2, so b squared would be 4. Okay. If you don't remember how to factor, you need to probably go back and brush up on that, because you will be using it quite a lot in this class. Okay. Now the x minus 2's cancel. Perfect. That was the thing that gave us trouble. Now we can go straight to plugging in 2. So let me do that down here for you. Plugging in 2, we'll get 2 squared plus 2 times 2 plus 4. So that's 4 plus 4 plus 4. Gives us 12. Okay. So either try and plug in the value. If that doesn't work, say you get 0 over 0, something like that, you've got more work to do, which so far we will factor and cancel and see what we get. Okay. On the other hand, what happens if we see something where that's not going to work? Say I look at the limit as x goes to 16 of 4 minus the square root of x over 16 minus x. Okay, now it's pretty clear. If I try and plug 16 in, I'm going to get 0 in the denominator, right? 16 minus 16, 0 in the denominator, and it will be 0 on the top as well, right? So we have a 0 over 0 case. The problem here is that we can't actually factor. You know, well, we can, but there's not a nice way to factor, right? This isn't going to factor. This isn't going to factor. So what do we do? Well, the answer is we use what's called a conjugating factor. All right. If you remember back in pre-cal or algebra, you had this technique to get square roots out of the denominator. And they told you it's because you can't have square roots in the denominator. They actually lied. You totally can. And we're going to actually end up with it here. Well, the conjugating factor and it may not be the proper term, it's what I like to call it, but basically a conjugating factor, if I have a plus b or an a minus b, either way, its conjugating factor will be the same thing, we just changed the sign. Right, change that middle sign there. Okay, and we multiply by the conjugating factor, this conjugate over itself. So multiply by conjugating factor. So I just take the piece that has the square root, 4 minus the square root of x, and then we're going to multiply by its conjugating factor, which will be 4 plus the square root of x. And we can't just do it on the numerator, we also have to do it on the denominator. Right. And so what we actually get is the limit as x goes to 16, 4 minus the square root of x times 4 plus the square root of x, all over 16 minus x, all over 4 plus the square root of x. Okay, we're going to FOIL this out, right? And when we FOIL it out, and what we're going to end up seeing, right, is that we'll get 16, okay, plus 4 times the square root of x minus 4 times the square root of x, then minus square root of x times square root of x, it's going to be minus x. And you see that these middle terms here cancel. Okay, and I'm going to leave the denominator exactly how it is. So you're going to have multiplying by the conjugate on top. And what's always going to happen is if you take, say something, say I had an a minus b, right? And I multiply it by its conjugate, I'm always going to get a squared minus b squared, no matter what they look like. So here, right, a was 4, b was square root of x. Here we go. We get down to, this is the limit as x goes to 16 of 16 minus x over 16 minus x times 4 plus the square root of x. Okay, here we go. That's 4 squared. That's the square root of x squared. Right? That's your a squared minus b squared. That's always going to happen, and that's why this method is actually useful. That's, you know, why it helps us calculate limits, especially because now this x minus 16, or other way around, 16 minus x will cancel. Now we can solve the problem, because now we get that this is equal to, right, the limit as x goes to 16 of 1 over 4 plus the square root of x. And now I can just plug the 16 right in, right, and get that this is 1 over 4 plus the square root of 16, which is 4, so we get 1 over 8. Okay, let's look at another example of this, right, where we have to use a conjugating factor. Let's say I want to find the limit as y goes to 0, okay, of the square root of 9 plus y minus 3 all over y. Now, we definitely can't plug in y because we'll be dividing by 0, and if we do it up top, I'll get the square root of 9 plus 0 minus 3, so that's 3 minus 3, so this is also a 0 over 0 case. And remember, with our 0 over 0 case, we basically have to factor and cancel, or use a conjugating factor. And when we use a conjugating factor, right, I'm going to make this entire piece A, this entire piece B. Oh, you can't see what I'm writing there. Let me slow this down a little bit. I'm going to make this entire piece A, this entire piece B. Right, so my conjugating factor is going to be the square root 9 plus y plus 3 all over the square root of 9 plus y plus 3 on the bottom as well. And how this helps is what's going to end up happening is when you FOIL this out, we're not going to FOIL it all the way out. It's just going to end up being the limit as y goes to 0, okay, of a squared. So that's the square root of 9 plus y squared minus b squared. B is 3 in this case. All over, and it's just going to be y times the square root of 9 plus y plus 3. And we're going to simplify this. Right? This will be the limit as y goes to 0, okay, of 9 plus y minus 9 all over y times the square root of 9 plus y plus 3. Okay, so the 9's cancel and the y's cancel. Now be really careful here, right? Really, I see this mistake a lot. This is going to be the limit as y goes to 0 of 1 over the square root of 9 plus y plus 3. And plugging in 0, well, now I can, because I won't get division by 0, I'll just end up with 1 over the square root of 9 plus 3, so we get 1/6. So this conjugating factor is actually really, really powerful. Okay, it can help. Usually you use it with square roots. So if you see square roots and you can't factor, and you get a 0 over 0, you should automatically think conjugating technique. But it can also work in different situations as well. Right? Say for example, this limit. Write it where you can see it. The limit as x goes to pi over 2 of sine x minus 1 over cosine x. Right, so here's a case where I can't just plug in the value, because when I do, well, cosine of pi over 2 is 0, sine of pi over 2 is 1, so we end up getting 0 over 0. Right, one thing you can do is write the arrows like that if you like, if that helps. So I can't really factor, right? These are trig functions, but I can actually try the conjugating factor. Right? Because all we do is change that middle sign. So this would be sine of x plus 1 over sine of x plus 1. And we use that idea, right, because sine of x is going to be my a, 1 is going to be my b. So when we multiply it out and simplify, we'll get the limit as x goes to pi over 2 of, this will be sine squared x minus 1. Right, sine squared, a squared minus b squared, which will be 1, all over cosine x. And this sine squared x minus 1 should look very familiar. In fact, if you think about the most important trig identity you have, which is sine squared x plus cosine squared x is equal to 1, if you move, say, the sine over, you get cosine squared x is equal to 1 minus sine squared x. And, well, we don't exactly have that, but if we flip the signs, multiply both sides by negative, we get exactly what we want. Sine squared x minus 1 is actually equal to, and remembering to write our limit sign, negative cosine squared x over cosine x. The cosines cancel, so I end up with the limit as x goes to pi over 2 of negative cosine x. And now we can just plug it in. That's negative cosine pi over 2, okay, which is 0. So whenever you see a 0 over 0 case with square roots, you should automatically think, or I should say sums of square roots, you should automatically think of the conjugating factor, that idea. But that's not the only time you can use it, right? It's often very useful when you see weird trig examples. So you might see a couple in your book that deal with that. Okay, well, last thing I want to talk about in this section is piecewise functions, right? How you define or deal with piecewise functions, limits involving that. And basically what it's going to boil down to is, well, piecewise functions are defined in pieces. We're going to separate it into pieces and look at the left-hand limit, the right-hand limit at each breakpoint. So, for example, let's look at f of x equals, let's say, the square root of 3 minus x whenever x is less than or equal to 2, and it'll be 3 minus 2x whenever x is greater than 2. Okay, so I want to find the limit as x goes to 2, let's say from the left of f of x. Okay. Well, to do that, first we need to find which piece this will live in, right? So the limit when x goes to 2 from the left, well, if I take a look at a number line here, let's say here's 0, here's 2. I'm coming at 2 from the left, so we're looking at things like 1.9, 1.99, 1.999. So that's where x is less than 2. Right? So we're looking at the values where x is less than 2 or equal to, but remember the limit is not where x is actually equal to 2, just strictly less than 2. So that's going to be this top piece. Right? So that will be the limit as x goes to 2 from the negative side of the square root of 3 minus x. Now, I do want this piece written, this and this. I want to know which piece you're choosing for each side. That's the important part here. Remember, the answer, the number at the end, isn't what's important. It's what you're actually doing. Okay? And so when we plug this in, this will be the square root of 3 minus 2. Okay? Which is square root of 1, so that comes out to be 1. And if you wanted to jump straight from here to here, you can. That's fine. Okay. Next up is, let's try it from the limit as x goes to 2 from the right of f of x. So once again, I want to know what side it is. So from the right, we go back to our number line. That's coming from the positive side. That's when x is greater than 2. Okay. And that's going to be the bottom piece. So that'll be the limit as x goes to 2 from the right of 3 minus 2x. So that will be 3 minus 2 times 3, or 3 minus 6, which is negative 3. Now, from looking at what we have here, what would you say about the actual limit as x goes to 2 of f of x, the two-sided limit? Well, clearly, it does not exist because the left-handed limit and the right-handed limit don't match. All right, what about f of 2? Now, this is where x actually equals 2. Right? So if we go back up let's look here. Where does x actually equal to? Well, that's at this top piece, so that will be the square root of 3 minus 2, which is 1. Okay, so here we go. The function itself exists at 2, it equals 1, but the limit does not exist because we have a jump. Right, from the left it's going to 1, from the right it's going to negative 3. All right, let's look at another example of this, just so you have another one. Let's look at f of x. Let's say is equal to x squared minus x. Can you see that? X squared minus x when x is less than 3, and 5x minus 3 over 2 when x is greater than 3. All right, we're going to do the same thing. The limit as x goes to 3 from the left of f of x. From the left, remember that's where x is less than 3. So that should be this top piece here. So that's going to be the limit as x goes to 3 from the left of x squared minus x. I want this piece written. Remember, I want to see which piece you're actually choosing. And that will be 3 squared minus 3, so that will be 9 minus 3, which is 6. Okay. Now let's check from the right. The limit as x goes to 3 from the right. Well, we've picked one side. That was the top piece. Here's the other side. When x is greater than 3, that should be what's left, right? So that will be the limit as x goes to 3 from the right of 5x minus 3 over 2. Even though it's obvious that you're going to pick this piece, I still want it written out, right? So that will be, when we plug in 3, 15 minus 3 over 2. So that's 12 halves, or 6. Oh, it's different here. Well, the left and right-handed limits match, so the limit as x goes to 3 of f of x, so this is from both sides, right, is 6, since these match. But what is f of 3? Well, if we go back, f of 3, well, remember this f of 3 is actually when x actually equals 3, as opposed to the limits. Less than 3, greater than 3. Here this is when x is actually equal to 3. And do I see an equal sign anywhere? No. So what's happening here is that this is undefined. So here's a case where the limit actually exists, but the function value doesn't. So this would be something like, if we graphed it, right, it would have a limit, but a hole. Whereas the previous example, where they didn't match, you would actually have something that looked more like this, where you actually have a jump. All right, so that's the last of what I want to talk about for now. Check back part 3, where we'll actually talk about the squeeze theorem. I'm separating that because it's a sort of funky little thing that kind of belongs to itself. Also be on the lookout for extra examples for this section.